I try to use this clock. Okay, it's better for me. So now 10:33. Okay. First of all, I would like to thank Suan, Shigui, and Jianhong for the kind of invitation. It's a great pleasure to attend this workshop because this is very special for gear work with. So before I start my talk, I try to say a few words about the gear and me, just in case this evening I have no chance to talk. Okay, we have dinner this evening. So actually, I cannot say happy which year because Shigui told me this workshop was postponed by 2 years. So now it's 71 or 72 or anyway, happy birthday to Gay. I don't know, 71 or 72 or 70. So congratulations on Gay's great achievements. For actually, I recall, I met Gay in 1994, first in Wuhan. At that time, Shigui and his former master supervisor, Professor Deng, organized an international conference on differential equations and mathematical biology. At that time, yeah. So we went for, at that time, I was working in Chinese Academy of Sciences in Beijing. So we all went to Wuhan. Over there, I met Morris Hirsch, Friedman, maybe Harl Smith, Geyer, anyway, a lot of friends there. And then after that conference, so I hosted Geyer in Beijing for a few days. Maybe this is the first time for Geyer to visit Beijing and even China in 1994. Yeah. So actually at that, because of that event, actually, so Jianhong, Geyer, and Herb, so they said, okay, next we will have a meeting in Edmonton. So you can come to Edmonton for the Butler conference. So after that, so Jianhong, Geyer, and Ferdinand, and later on, Joseph Su also joined in. They invited me to visit Canada before that conference. So McMaster University is my first stop when I came to Canada. And then second stop is York, third stop is Alberta, and then I went to ASU from Alberta. So I want to take this opportunity to say sincere thanks to Gail, because Gail gave me a lot of help, in particular her constant encouragement. Even when I working in ASU, when I try to find some academic job in North America, Gail, of course, other friends, Gail also wrote very positive and very strong positive recommendation letters for me. Even last year for some events, she also wrote a letter for me. So thank you very much for your kind of help. And here, actually, when I was in McMaster, I did work with Gail. So I try to use this one. This is about the n-species computation model in a periodic chemostat. But this paper was published a little early, but this work was done when I was in McMaster. Oh, by the way, in the fall semester of '94, I went to McMaster. At that time, Gail was taking sabbatical leave, but Ralph Smith was there. So he was just the master student of Gail at that time. So over there, I met Ralph Smith. I also taught the OD course for him and another classmates. Yeah. So here, maybe I cannot show. Actually, I want to show this information. So how can I use them? I try to click this one. How can I click this? Maybe that's what I want to click this link to show this paper with. Oh, we'll click this one. I guess here in field we can go to AMS math review. I guess you click anywhere here. That's okay. Yeah. Can we click this link? Maybe save some time. That's okay. So anyway, so I copy this link from math review, try to show the title and the equation and the episode from this paper. That's okay. And actually, I did a lot of picture with gear when we were in Wuhan and in Beijing. But I'm sorry, so at that time we have no iPhone. I didn't bring all of the album with me. Now that album is in my home in China. Okay. So anyway, but here I want to show you a recent, very recent picture. So at in June 5th, so Gear and Harry were at the CMS summer meeting in Xinjiang. So in June 5th, so we invite Gear and Henry to go to our home to have lunch. So after lunch, we have Chinese tea there. My wife made a picture for us three. Okay. That's no, not our city. Yeah, not Xinjiang city. Okay, so anyway, so happy birthday to Gear, and good wishes to Gear and Henry. In Chinese, we also see, in Chinese we see 永远年轻，所以是 young forever. Okay. My talk, I try to give a motivation for this work and try to present this theory for R0, for autonomous and periodic delay equations, and try to give a simple application. And then I give a remark. Actually, so why I did this remark, because last year, Jiang Hong asked me a question, so I wanted to answer his question positive, but maybe he's not here. Anyway, you will see what's that remark, okay? So here, as everybody knows, this is a standard SIR model. So last time I talked with Shigui said, actually this model is a simplified version of this famous paper. So not the original model. So for SIR model here, this R is effectivity rate, and A is a removal rate. So clearly, 1/A is the average infection period. So at that time, so they want to ask, so suppose we have a typical infected individual. We want to see during the period of infection, how many new infective individuals can be infected, can be produced. So use this definition, so they use this idea. So, okay, here is one individual. So this contact with S0, this is initial size for susceptibles. And then you, this is one infected individual, this is a susceptible, and then this is a per unit time, you have these new infected individuals. But 1/A is the infection period, so this times period, 1/A, you get during the whole infection period, you have these new infected individuals coming out. So this number now is called R0. So actually, the KM, they showed that, so when R0 is less than 1, there is no epidemic outbreak. If this R0 is larger than 1, there is an epidemic outbreak. So mathematically, actually, you can see for this model, so this, you have a disease-free equilibrium, S0, 0. If you do linearization for this model, you choose the I equation, you just change this S into S0. This is a linear equation for infected variable I. And you can write this into two parts, first F and I. So this F is R times S0. You can regard it as the infection rate. And this part, you can take this V as A. So this part means, without infection. So we have this kind of internal transition or internal evolution. You can use this OD to describe this internal evolution. So this is from the classical model, we have this observation. And actually, so this is the Arnold theory now is well developed. I will try to save some time because everybody here is an expert. Everybody know Arnold, so I try to save some time. But here I want to mention several survey and review papers here. I guess maybe, I guess Jian and and Robert was our audience. So this is a survey paper earlier, and this one, and even Jim Cushing and Old Dickman also wrote a survey paper, and later on, so in 2017, Pauli also wrote a survey paper published in Jiang Hong's journal. Okay, yeah, actually, it's in the second edition of my book, so I also included R0 for the delay equation, for the reaction defect equation arms, and some complicated epidemic model. So here are the most important thing in this area, in my opinion, is Otto Dickman's and his collaborators' idea. This is called next generation operator, or at the very beginning called next generation matrices. So this idea, because we have a multi-population, multi-species, we have compartments. You can also see one typical infect, can infect how many new infectives. That is not easy to compute. For example, you have a multi-species, you have more compartments. So they use this idea, so-called next generation operator idea. So this is a positive matrix. They use the radius of it to define R0. And for the development, I guess here, so James and Pauli, they developed this idea to the OD model. They get a very nice formula. Now everybody know this formula: F times V inverse, and take the spectral radius, you get R0. And for the periodic environment, actually, by the way, this paper, I tried to see the citation, seems numerous citations for this paper, maybe more than 5,000, I guess. Okay, and later on, so these two guys, they consider the seasonality. Suppose you have some coefficients are time periodic, how to define R0. So in this paper, they have some idea. So we try to use a space of periodic functions to define something like the next generation operator, and then you take the spectral radius of it to define R0. So this, and later on, so Wendy Wang and I, so we studied the periodic OD model. We give the definition for R0, and we give the characterization of R0, and we give the algorithm how to compute R0 numerically. And later on, guys, host team from ASU, he published a very nice paper using the spectral bonds for the linear operator to relate the R0. And later on, these two people further discussed R0 for the periodic case, and even this author is Inaba was a former person of Otto Dickman. He used another operator to unify autonomous and periodic case biologically. So, and then since host team's work, there are a lot of applications for autonomous reactive equation, and for the time delayed reactive equation, and even for almost periodic models. Here I want to mention a few people for the so in the earlier time, okay. And here I wanted to say, unfortunately, hosting the idea or theory cannot work for time delayed model when you have time delay and time period at the same time. Here is one main idea why hosting theory cannot work. For example, so you have this linear equation here. So A and B are constants. B is positive. We know this equation admits the comparison principle because B is positive. So Hall-Smith proved that the stability of zero solution of 1.2 is equivalent to the stability of this OD system. OD, if you ignore this tau, in other words, you can take tau as 0. You get this OD. So this OD is easy to do the stability. When A plus B is positive, you have instability. When A plus B is negative, you have stability. However, this is not true for periodic case. Suppose you change A into AT, B into BT. Again, suppose BT is positive. This means 1.3 still admits the comparison principle. You can maybe when we ignore tau, you get this OD. Here no tau, and you have AT plus BT. In general, this is not true. Here I want to mention Gurgley's earlier work. I like this short paper very much because in this paper, Gurgley gives the counter example to show we do have the periodic linear equation. The stability of zero solution cannot give the stability of this term deleted equation. They are quite different. Of course, in this short paper, Gurgley also obtained some condition for, and one condition we can use this OD stability to get this delay equation stability. This is one main reason why. So when we have time delay and time period, you cannot use Hostin theory. This is another reason. Of course, there are other technical reasons. So this is our purpose. Our purpose is to try to develop this R0 theory for time delayed and periodic epidemic models, and try to develop a general algorithm to compute R0 numerically. Okay, so here, this is our setting. So because I know so many of you are familiar with FD, so I try to be brief here. So we have this tau, like space for this phase space. This is the standard notation U sub t from delay equation. And then, so we try to consider this linear equation here, 2.1. The reason why I consider this 2.1 is as follows. So when you have a epidemic model, usually you have a disease-free equilibrium or disease-free periodic solution, and then you do linearization. You look at the infective individual variable, you get this kind of linear equation. So here, so f is functional. This is because the new infection at the time t depends on the infected individual between t minus tau and t. So this is called the infection part. Infection part is here. But here, for the internal evolution, so we suppose no time delay. For example, death rate, natural death rate, disease-induced death rate, and the transition among compartments. Usually, no time delay. I will give a remark at the very end of my talk. And then, so here, without infection, so the internal evolution, so is governed by this linear ODE. Here, I suppose functional FT and matrix VT are time periodic with common period omega. Okay, so the idea is this. Okay, so here is of course, if you return to population growth model, you can linearize your system at a zero solution. See, you have n types of n patch. You get a linear equation. You can put new production this here and put other terms here. So for both population growth model and epidemic model, you can always get this kind of linear system 2.1. Okay. So this is a standard assumption for the functional FT, and with this assumption, you have the uniqueness. You have the well-posedness of solutions. Here, because this is non-autonomous equation, we must use the initial term S. For autonomous case, we always choose S as 0, but for non-autonomous case, you must consider initial term. So I use S means initial term, so initial value, this is a solution, this is a linear equation, okay? And then I use this notation. So suppose this U is defined this way, this is called evolution family or evolution operators associated with this periodic linear equation, okay? And then for this internal evolution, so we use this fundamental matrix or again evolution operator of evolution matrices. Here, initial term is S, so you have this phi. For this kind of evolution operator, usually we can define the so-called exponential growth bound to describe the stability. So this is definition for the exponential growth bound here. This number is positive, means solution is not, zero is not stable. This number is negative, means zero is stable, okay? And then so two assumptions here. First, this infection functional is a positive operator. This because this part we put infection there. So this operator ft for each t, this operator ft is a positive operator. So, okay, and because we put the natural death, disease-induced death, and the movement among patches, so this meter minus v is cooperative because the death rate is on the diagonal. So this minus v is a cooperative matrix. Of course, without infection, this linear system, let me see here. So this linear system, so without infection, we suppose that the solution decay to zero. In other words, the zero solution is stable. So we must assume this exponential growth bound omega phi is negative. So these two assumptions so make sense biologically. Okay, we use this assumption to develop this theory. Okay, and here suppose we have a periodic. Suppose we consider a periodic environment. Suppose Vt is periodic in T. This is initial distribution of infectious individual at the time T. Okay, for any given time T, let's consider the earlier time before T. So suppose I choose S positive. So at the T minus S moment, so we have, this is our new infection. Okay, and then so from T minus S, we do internal evolution or internal transition from T minus S to time T. So this term means the distribution of those infected individuals who were newly infected at the time T minus S and remain in this infected compartments at the time T, from T minus S to T. And then for all earlier time means you do sum for all S. So we have this sum for S. So this means the distribution of a cumulative new infections at the time T produced by all of those infectious individuals, so introduced at all previous time to T. Of course, you can do another expression. Here I do infection first and then do evolution. Of course, you can do evolution first and then do infection. They give the same number or not. So I won't write that detail here. Some first chicken and then egg, or first egg then chicken. So actually we prove that R naught is the same. So here I didn't write another operators. Here I do infection first and then do evolution. You can do evolution first and then do infection. Okay, and then clearly, so if we do this, I don't like this point. So here, suppose consider a continuous and omega periodic function. This is a Banach space with the maximum norm. And then clearly, we can define this operator. So this operator L maps periodic function V into another periodic function of T. So this is an operator, so on this Banach space C omega. And then we define this spectral radius of L as R naught. So I prefer to call this basic reproduction ratio, because this is, this means you have this distribution, after infection you have another distribution. The correspondence is an operator, so the radius means the maximum ratio. We call this maximum ratio as the basic reproduction ratio. Of course, some people prefer to use the number. So I recall I discussed this with Odo and Hall. He said we all agree you use ratio rather than number. Of course, they are real number, but the ratio is more reasonable because this is operator. Okay. And then so I prove this one. So here, so this R naught can give the stability for the zero solution. So in other words, so this R naught, so equals 1 means this Poincare map or periodic map from 0 to omega, the spectral radius is 1. This when R naught is larger than 1, this spectral radius is larger than 1. This means so zero solution is unstable. When R naught is less than 1, this radius is less than 1 means zero solution is stable. In other words, R naught minus 1 has the same size as R of this Poincare map or periodic map radius minus 1. So this gives us the stability equivalence. This is what we want. Otherwise, this R naught is not good. We want to use R naught to do the at least the threshold for the local invasion of the disease. Okay, and then we further study how to compute R naught, at least numerically. So we can do this one. Introduce a parameter lambda here. Again, here this is the equation, and here suppose this is the evolution operator with parameter lambda. So when you take S as 0 and T as omega, this means the Poincare map for this system 2.3. And we prove that this R naught larger than 1, then this R naught must be the unique solution of this equation. So for some value lambda, this radius equals 1, that lambda must be R naught. So this gives us how to compute this R naught numerically. You try to solve this this equation for lambda, and then that lambda is R naught. But here actually, so I try to return. Actually, one of the main purpose for me to choose this, I want to emphasize consequence of this theory. Return to autonomous case. Okay, so when f is independent of t, when v is independent of t, we have autonomous case. So v, so this is function from C to Rm. So from this C, from this f, I can define a matrix. I use f hat. In other words, matrix means this is from linear operator from Rm to Rm. This is m by m matrix. How to define this matrix? The idea is this. So for any vector in Rm, you regard this you regard u as a constant function of theta. I use u hat. And then f is a function from C to Rm. Okay, you use f of u hat. You get a vector in Rm. So this f hat so maps vector u to another vector. So this f hat is a linear operator from Rm to Rm. In other words, this is a matrix. With this notation, so I can give you the formula. So for the autonomous time-delete models, we have a formula for R naught. R naught is here. You compute f, get f hat, and because v is a matrix, so you do f hat matrix times v inverse. You do spectral radius, you get R naught. When tau is 0, this means when tau is 0, so this clearly this f hat equals f. So you return to James and Pauli's formula. So when tau is 0. So this is I like this very much because a few years before 2017, when I met Pauli said, "You guys developed the R0 to period ODE. How about the delay equation?" I said, so no general form for delay equation model. I cannot do it. So after I finished this work, I sent this work to Pauli. Pauli was very glad. Said, okay, so now for autonomous delay equation, you guys have a formula for R naught. That's very useful for delay equation. So I'll give you a simple example here. Suppose you do for epidemiology with time delay, you do linearization around the disease-free equilibrium. You have this linear equation here. Okay, so here you have tau 1. Here you have the distributed delay. Okay, and here you have internal evolution minus v is a matrix. And then now, so you how to compute my matrix f hat? F hat means this one. F hat means you just treat vector u as a function u hat, you compute f of u hat, you get another vector. Okay, so that idea tells, okay, so if this is f phi, you take phi as vector u, so u is element of theta, so you put u out here, here u out, you get this k1 plus this integral. This is my matrix f hat. So you can see R naught equals f hat times v inverse, and then you take spectral radius. So this is a very nice observation. So I recall, so in Michael's talk, he said, so the final set is independent of R naught. Very likely, R naught is the same if you ignore time delay here, because if you ignore time delay tau 1 and here no delay, actually you get the same R naught with ODE. However, the other term, the coefficient maybe depends on time delay. I recall many years ago, Gear argued for some model. Okay, many people forget e to power minus mu times tau because that's the survival probability. Also here you can ignore tau here, but in K1 or K2 you may have tau. For example, survival probability e to power minus mu times tau is there. So I guess very likely for your models you have this formula, you have the same R naught, but I'm not sure why you have the same final size because other terms may depend on delay tau.
The ones we tried is independent coefficient.
Okay, in that case you are right. In that case, at least R naught is the same. Because here I just ignore time delay. You see here, so you can see here. You see this matrix. You just take constant vector. You compute this.
We just have to work harder to consider that case. That's all.
Okay. Yeah. Okay. Anyway, I give a comment on your talk. Okay. So anyway, so here of course we can do the spatial model. You can put the diffusion into the minus v. You get an operator, and then do this kind of generalization. And here, let me see. We start 3 minutes late, right?
11:13.
Okay, yeah. I still have 7 minutes, right? Okay, yeah. So here is our idea to compute R naught. For time period case, it's not easy to have the formula for R naught, but we can do this numerically. So here, for a linear operator, so suppose it's positive, we have this observation. If you take any strongly positive element from the interior of the positive cone, you compute LV n-1, and then over the norm of it, you get Vn, and define An this way. And if this sequence of numbers has limit, then the radius of L equals this limit. So use this idea, we can compute R naught very quickly. Why? You solve this equation for given lambda, you choose this L as this point remap, and you compute the value numerically, and then you use the method of bisection. So half means each time you do bisection. For each middle point, you compute this value. You can do this numerically. So actually here, this information, because many young people send me email to ask the algorithm and even ask for the code for the R naught. So my former student Li Zhao, they chose 4 examples. Very typical: ODE, PDE, periodic, or time delay, random diffusion, or non-local dispersal. So this guy Li Zhao chose 10 examples and wrote the algorithm and the code and put it on the website. So here I cannot click this one. If you click this one, you can see 10 examples to cover everything for the epidemic model. If you want to compute R naught numerically, you just modify slightly that code. You can compute R naught for your model. In particular, for periodic case, for time delay case, or for the reaction diffusion equation, you can use this this code on the website. Okay, and as Huiping said, I have a few minutes. I omit this detail. This is a model for the malaria model with periodic latent, and with and then for this one you do the linearization. Around this disease so-called disease-free periodic solution, you get this infect human being and infect mosquito, and then you write the functional F here, and you write this matrix V here. Of course, you can define R naught and compute R naught numerically. And finally, so for this model, we have very nice threshold result in terms of R naught because of the special structure of this DD model. And finally, I want to give a remark here, because last year, so Jian Hong told me, so if in the internal evolution you have DD, how can you define R naught and how can you compute R naught? And actually last year, so when Dr. Xiaoqiang Wang, when we discussed the so-called target reproduction, we put some terms from F to V. So in minus V, again, we have time delay. We have this problem. So recently, we solved this problem completely. So you can have some, for the internal evolution of internal transition, you can have some time delay. However, make sure this system is monotone. Make sure this system admits the comparison principle. And then we can do the similar R naught definition. We have similar computation for R naught. Even the earlier two theorems, similar 1 and 2, also work for this case. The key here is a basic assumption for this. This is an infection functional. This minus V now is not a matrix anymore, it's a functional as well. And then we do some basic assumption, we can do this or not. Okay? So actually here today my talk is mainly based on this paper. So this is my own paper in 2017. The malaria model with the periodic incubation period. This model is this is from my paper with earlier student Xiaoqiang Wang. And for the general algorithm and general development, so we have this paper here. And I mean for this, if for the internal evolution, if we have time delay, this paper is now still is in review. So we put this in the appendix of this paper to see how if you change VT into a functional, again under some conditions, this theory is still valid. Okay, so I stop here. Thank you.